Now, let's look at another example. In this example, we are told that AB is a diameter of the circle with center F. We are also told that AB intersect DC at G, but they didn't say that it intersected at midpoint, and they didn't say it intersected perpendicular. They didn't talk about that. Therefore, already we know that theorem number 1 is not there, because we can assume the only time we can say theorem number 1 is there, it's when we are told that this is the midpoint, G is the midpoint. Then we can say we've got theorem number 1. Therefore, we can't say we've got theorem number 1. So in this problem, we are told that AB is a diameter of the circle. We are also told that FD and FC are drawn. We are also told that BA bisects D angle AC. It means that BA cuts this angle into 2 equal halves. So it means that this angle is equal to this angle as well. When they say AB bisects D angle AC, it means that AB cuts this angle into 2 equal halves, into 2 equal angles. Now, we are also told that B angle DG or D angle BC is 37 degrees. We are told to find 3 other angles equals to D1. But first, before we can find 3 other angles that equals to D1, we still follow the same thing that we've been doing to eliminate all the theorems which are not in this problem, so that it becomes easy to solve a problem. Now, we first ask ourselves, are they chords? Yes, they are chords. Most times they are chords. Are they cyclic chord? They didn't talk about any cyclic chord here. Are there tangents? No tangents in this problem. You can see no tangents. Therefore, theorem on tangents are out. Theorems on cyclic chords are out. We are only left with theorems on chords. Now, we first ask ourselves, is there a line drawn from the center to the midpoint of the chord? They never talked about the midpoint here. Or they never talked about a line drawn perpendicular to a chord. Therefore, theorem number 1 is out in this problem. Now, theorem number 2, is there angle at the center 2 times angle at the circumference, or twice angle at the circumference? I can see that there's an angle at the center, there is an angle at the circumference. Therefore, theorem number 2 is there in this problem. Now, do we have a tangent as a diameter? Yes, we do have a diameter. Therefore, we do have theorem number 3. Theorem number 3. Do we have theorem number 4? Angles at the same segment? Yes. This chord subtends this angle there. It also subtends this angle there. This chord. As you can see, this angle, it's subtended by this angle. It is also subtended by that. Therefore, theorem number 4 is there. So theorem number 1 is not there. It's the only theorem which is not here. And theorem number 5 and 6 and theorem number 7, 8, 9 are not there. Theorems on tangents and theorem on cyclic chords are not there. These are the only theorems which are here on chords. Now, they say to us, we must find 3 other angles equals to D1. As I am looking at this problem, I can see that this angle here, this arc, subtends this angle. You can see this arc, it subtends this angle, which is D1. This arc subtends which other angle again? This angle. Because look, there, look, there. It subtends this arc subtends this angle. This arc, it also subtends, look, it also subtends this angle there. Therefore, we've got angles in the same segment. Therefore, angle D1 is equals to angle A1, angle A2, because it's equal to angle A2, which is equals to 37 degrees. Why? Angles at the same segment. We can say seg if we want. They're in the same segment. Look, subtended by that. Look, subtended by that. Therefore, this angle is equals to that angle. Now, another angle that is equals to D1, because they said they want 3, is this one. Since we're told that BA bisects this whole angle, this line bisects this whole angle. It means that this is equals to that when it bisects. Therefore, angle A2 is equals to angle A1, which is equals to 37 degrees. Why are we saying that? It is because BA bisects D angle AC. That's what we were told, that BA bisects D angle AC. Another angle that is equals to angle D1 is this angle. Since this angle here, angle A1, is equals to this angle there. Since we've got an isosceles triangle, this side and this side are equal, radi. Therefore, this angle is equals to that angle. Therefore, angle A1 is equals to angle D3, which is equals to 37 degrees. Reason, angles opposite equal sides. Which sides are those? We must also include that. Which sides are those? It's DF, which is equals to FA. If I didn't include it in the previous example, we should include those two sides which are equal. If I didn't include, please include them in your notes in the previous example. Now, we now have this angle which is also 37. If we wanted, we could have said this angle is equals to this angle C2 as well, which is also C2 is equals to 37. We still have angles opposite equal lengths, where FC is equals to FA if we wanted. But they said 3 angles that are equals to D1. So we found them. Now we must prove that DG is equals to GC. So it means that we must prove that this is equals to that. And how can we prove that? We know that theorem number 1, a line drawn perpendicular to the chord, it means that it bisects the chord. Oh, so it means that if we can find that G1 or G2 is equals to 90 degrees, then we got the converse of theorem number 1. Then we will know that this is perpendicular. And if this is perpendicular, it means that this line bisects this line. Therefore, this is equals to that. I've already proved this thing by just explaining. But now, there is the writing of this. We need to find angle G1 that is 90. Once we find that angle G1 is 90, then we know we've got the converse of theorem number 1. Therefore, let's find angle G1. But for me to find angle G1, I need to find this angle, which is F1. And F1 is equals to this angle here plus this angle here. It's an exterior angle, since you can see it's an exterior angle of a triangle which is equals to the sum of the opposite interior angle. Therefore, we can write it, angle F1 is equals to angle A1 plus angle D3. This angle is equals to this angle plus that angle, exterior angle of triangle AFD. AFD is equals to the sum of opposite interior angles. Exterior angle of triangle ADF is equals to the exterior angle of triangle ADF is equals to the sum of the opposite interior angle. Now, we do know angle A1, sorry, it must be angle A1 there. We do know angle A1, which is equals to 37 degrees, plus angle D3. These angles are equal. We've seen, which is equals to, obviously we've seen there, which is equals to 37 degrees. This plus this is going to be 74 degrees. This angle here in green is 74 degrees. Now, we can find this angle here, and we know that this is a diameter, and if this is a diameter, it subtends an angle there at the circumference. Therefore, this angle is subtended by a diameter which is equals to 90 degrees. Therefore, we can find angle D1 plus angle D2 plus angle D3 is equals to 90 degrees. We've said it that there's theorem number 3 there. Therefore, why are we saying this angle plus this angle plus this angle is equals to 90 degrees? Because this whole angle is subtended by a diameter. And this whole angle is the same as adding this plus this plus this. We are getting this whole angle, which is subtended by a diameter. Therefore, angle subtended by a diameter. A diameter. Angle subtended by a diameter, obviously it is 90 degrees. We need D2 because we do have D1, we do have D3. If we can find this angle, then we can use this angle plus that angle to find angle G1. Now, we find angle D2. We know angle D1 is 37 degrees, plus we know angle D2. We don't know angle D2. We are looking for it. Angle D3, we know it is 37 as well, which is equals to 90 degrees. Now, angle D2, 37 plus 37 is going to be 74. Therefore, it's going to be 90 minus 74. Now, 90 minus 74 is going to be 16 degrees. It's 16 degrees. Now, we do know that this is 16 degrees. We do know that angle F1 is 74. We do know that this is 74 degrees, this angle there. We can find this angle there. And how do we find that angle there? I'm just going to erase here. We find this angle. We say angle D2, angle D2 plus angle F1 plus angle G1 equals to 180 degrees. Why is this? We are adding this angle plus this angle plus this angle, which is equal to 180 degrees. I'm going to write the reason below: sum of angles on triangle DFG. DFG. This is the triangle we are talking about. Sum of angles on triangle DFG. Now, we can find our angle that we are looking for, which is G1, obviously. Now, we do have D2, which is 16 degrees, plus we do have F1, which is 74 degrees, plus we want angle G1, which is equals to 180 degrees. Now this is 90 plus angle G1 equals to 180 degrees. Angle G1 is equals to 180 minus 90, which is equals to 90 degrees. Now we know that this is 90 degrees. Since it is 90 degrees, it means that a line is drawn perpendicular to the chord. Since a line is drawn perpendicular to the chord, therefore it means that it bisects their chord. Therefore it means that this is equals to that. Therefore we can conclude, I just want to erase here, or I can write it here. Therefore we can conclude that DG is equals to GC. Why is that? It is because the converse of theorem number 1, where it says if a line is drawn perpendicular to the chord, then this line bisects the chord. I can just give the reason as therefore FG is drawn from the center to, or is drawn from the center perpendicular to the chord. That's the reason why we're saying this is equals to that. Since a line is drawn from the center perpendicular to the chord, then we know that it bisects the chord. Then we know that DG is equals to GC. Then we know that it bisects the chord. Now, the next question is saying that if it is further given that the radius, is 20 units, they say we must find BG. We must find BG. So we must find this length here. Must find this length here. Here. Must find this length there. And for us to find that length there, we can find FB. We can find FB. And by finding FB, or we can find FG. We can find FG. And by finding FG, then we know the whole of this radius minus this, we are going to get that. The whole of the radius, therefore BG is going to be the whole of this radius minus this, we're getting BG. And for us to find FG, I do have this angle here, 16. I do have this angle in this triangle here. In triangle DGF, in triangle DGF, for us to find this length here, we need to use opposite. We do have the radius, and the radius is given to be 20 units. Therefore, there's our angle 16. Therefore, I can use opposite over hypotenuse. Hypotenuse is always opposite 90 degrees. Opposite, which is sine. Sine 16 degrees is equals to opposite, which is this. FG is equals to FG over hypotenuse. And our hypotenuse in this case, it is DF or FD. DF or FD. Now, we can find FG because that's what we are looking for. We are looking, in an actual fact, we are looking for BG. But it will help if we start by finding FG. Then we can find BG. That is why there's FG there. FG. This is over 1. I can cross multiply. This multiplied by this, I get FG. This multiplied by that, I get FD, sine 16 degrees. But we know FD, which is our radius. FD, it's our radius, which this is also equals to FD. Now, we've got 20 sine 16 degrees. When we press the calculator, I think I remember it's about 5.51, I think, units. If I still remember correctly, 5.51 units. Now, since I got this, now I can get BG, because BG is equals to FG, which is the radius, FB, the whole of this is the radius. The whole of this is the radius. Is equals to FB minus, we've just found our FG, which is this part, minus FG. We're getting what we are looking for, which is BG. Therefore, BG is equals to the whole of the radius minus this, we're getting this. The whole of this minus this, we're getting that. Therefore, we have 20 units minus our FG, it's 5.51, which is equal to 14.49 units. Now, we have found BG, of which that's what we were asked to find. If we wanted, we could have found this by using this angle here. And this angle here, for us to find this length here, FG, then we're going to use adjacent over hypotenuse. And adjacent over hypotenuse is cos. So we're going to say FG, we're going to say cos 74 degrees is equals to adjacent, which is FG, over hypotenuse, which is, our hypotenuse is FD, which is FD. Therefore, we're going to find, cross multiply as well, this is over 1, FG, which is our FG, is equals to 20 cos, 74 degrees, which is going to be 5.51 units. then we're still going to use the same thing there. We're going to say BG is equals to FB minus FG, which is 20 minus that, which is the same thing as there. That's if we wanted. Now, there are problems where our trigonometry is not going to work. But here it works perfectly because our triangle DFG is a right-angled triangle. Yes, you will see, I'm going to show you an example next time where a right-angled triangle also, we cannot use what we have used here in that particular triangle. I'm going to show you the next example that probably we are going to do. I'm going to show you that trigonometric ratios sometimes do not work in a geometric problem. Here it worked because our right angle triangle, its length, the sides are properly defined. But you will see the next time when your sides are not properly defined in a right angle triangle, then trigonometric ratios where we use that, trigonometric ratios where we use that, trigonometric ratios where we use that, trigonometric ratio, even here trigonometric ratio does not work in such problems. You will see an example that it does not work sometimes. That's that.